Smart contracts are where blockchain stops being just a ledger and becomes a policy engine. In this module, we'll look at how on-chain logic can reliably enforce rules, align with law and regulation, and what it takes to trust that code in production. In traditional systems, policies and agreements mostly live as documents. People read them, interpret them, and then manually enforce them in code and processes. Blockchain introduces a different idea. Encode those rules directly as smart contracts that run on a shared ledger. Think of them as automated business rules and trust policies. Once deployed, they can autonomously enforce who can do what, when payments move, and when access is granted, while leaving behind an immutable, jointly auditable record. When we use blockchain as trust infrastructure, precision in modeling is non-negotiable. Treat every process as a state machine. A record starts in a draft state, moves to an active, enforceable state when it's signed and deployed, then eventually reaches a closed state when a specific trigger occurs. Your job as an architect is to mirror that real-world lifecycle exactly. No hidden states, no ambiguous transitions, no sometimes we do this branches. Complexity is the enemy of security. Every extra path is another place for bugs, disputes, or fraud. Encode clear preconditions and postconditions so the ledger can automatically reject impossible or unauthorized transitions. Separation of concerns is one of the most important ideas you'll reuse across this entire course. Rather than designing one big tangled system, you break responsibilities into cleanly defined components. For blockchain-based trust, that means core logic is not tightly coupled to how or where data is stored or how access is enforced. Each concern has its own layer and interface. This isolation improves security, makes audits easier, and lets you upgrade or replace parts without destabilizing the whole network. Blockchains are great at one thing, not changing. But our policies, regulations, and business rules change all the time. To reconcile this, separate two concerns: where state lives and where logic lives. Users always talk to a stable proxy address. The proxy simply forwards calls and state to whatever logic contract it's currently pointing at. When requirements evolve, you deploy logic v2 and update the proxy's pointer, instead of migrating all the data or breaking integrations. The critical safeguard is governance. A multi-sig or committee controls who can change that pointer under clear policies and audit, so upgrades are possible but not arbitrary. Smart contracts are often described as code is law, but in enterprise and government settings, that's never the whole story. You still have real contracts, regulations, and service-level agreements that sit above the code. The key idea is alignment. On-chain behavior has to faithfully implement off-chain obligations. That means embedding compliance checks directly into logic and designing clear paths for dispute resolution. When something goes wrong, parties must be able to pause actions, freeze assets, or escalate to human or legal processes. When we talk about blockchain risk, smart contracts are often the most fragile part of the system. A single bug can move real money, leak sensitive data, or permanently lock critical records. The threat landscape is also different from traditional applications because contracts are public, immutable, and automatically executable. Attackers actively scan for weaknesses and can exploit them at scale. As architects, we need to understand these bug patterns so design, review, and governance all assume contracts will be targeted. For blockchain-based trust, security has to be baked into the lifecycle, not stapled on at the end. Start with specification. Define explicit threat models, invariants, and abuse cases, so requirements already encode security. During coding, follow the checks, effects, interactions pattern, validate inputs, update internal state, then call external components to avoid reentrancy and race conditions. Apply least privilege everywhere. Separate operational, governance, and break glass roles. No single key should give unlimited God mode control. In testing, exercise negative paths, adversarial scenarios, and consensus edge cases. Finally, use audits to validate assumptions, configs, and governance, and feed findings back into the next specification. For blockchain-based trust infrastructure, assurance has to be layered. At the foundation, use automated tools, static analysis, linters, and fuzzing to catch the obvious and the low-hanging fruit at scale. They're cheap to run continuously, but they miss context and creative attacks. Above that, rely on human expertise. Independent security reviewers can challenge assumptions, spot architectural flaws, and connect the design to real-world threat models. At the top, when the risk justifies the cost, add formal verification to mathematically prove critical properties of protocols or contracts. The mindset is trust but verify. Combine these layers, none of them is sufficient on its own. Before any blockchain-based trust system goes live, treat certification as a hard gateway, not a formality. Define a certification record template and make it mandatory for every network, smart contract, and major configuration change. Your checklist should cover 3 dimensions. First, all security baselines: node hardening, key management, access control, monitoring. Second, functional requirements: core flows tested end-to-end, including failure and rollback paths. Third, regulatory and policy checks: data protection, records management, and sector-specific rules. Only when all 3 are evidenced and signed off by the right owners should you allow deployment to production. For blockchain used as trust infrastructure, the deployment path must be tightly controlled. Think in 3 stages: development environments for experimentation, a test network that mirrors real conditions, and only then the production network. Each stage should have explicit exit criteria, including security and compliance checks. Once live, assume something will eventually go wrong. Build in operational breaks, rate limits to contain surges or abuse, continuous monitoring with alerts for anomalies, and, for critical contracts, a clearly governed pause or emergency stop mechanism. The goal is not just launching the network, but ensuring you can observe it, throttle it, and safely intervene when behavior deviates from expectations. Smart contracts aren't forever. For regulated enterprises and governments, you have to design their end of life as carefully as their launch. Plan for deprecation. You need a clear way to mark contracts as no longer active, so new workflows don't depend on them. Define migration paths so data, user access, and business logic can move safely to new versions or new platforms. And preserve code and audit trails so past decisions remain legally traceable. Engineering trust with blockchain is about deliberate design, not hype. In this module, you've seen how policy engines encode rules, how precise architectures align ledger, identity, and data flows, and how layered security protects nodes, keys, and smart contracts. You've also seen why governance and operations must be designed as carefully as the protocol. Take these lenses into each new project, and you'll be ready to build resilient infrastructure for digital trust.